In this video, I will show how to run quantum circuits on actual IBM quantum computers. And what I will do, I'll take a simple example circuit, actually the one that we just studied in the last video, that helps us transfer a single qubit state from one physical qubit to another physical qubit. And I will also show the circuit how to simulate it using Aer Simulator. And for both of these, we will use a special structure in qiskit that has been introduced in qiskit 1.3, actually 1.2, 1.1 as well, which helps us submit jobs to simulator and IBM quantum computer in an easier way, where we can submit many circuits in a single job. So for that, let's program using Colab, and for that let's go to colab.research.google.com, and suppose we start a new notebook. And what I will do is set up this notebook, and this notebook is also available for download from GitHub link given in the description of this video, and you can just download the notebook and follow along if you like. Let me start by installing the required packages, because whenever we have a new connection in Colab, we have to install the required packages. So I need qiskit for basic functions and qiskit Aer for Aer Simulator. PyLatex ENC will help us plot circuit using matplotlib option, and this qiskit IBM runtime, this will help us access IBM quantum computer, and also a special class sampler version 2 that will allow us to run circuit in an efficient manner. So let's press shift enter to install. So while these installations are happening, let me go to quantum.ibm.com and show you the available quantum computer. Actually, when you will be doing it for the first time, you will be landing on this page. So if you have not created IBM ID already, so you will have to create IBM ID. I have already done it, so I will go ahead and log in using my Google account. And once you log in, you will land on a dashboard page that shows summary of your account. For example, how much time you have left and how much time you have used. So every month you get 10 minutes of free quantum computer use from IBM. And you can also see the jobs that you have already run over here. And there is this important thing, job ID. For example, this job ID that I ran today, it's already completed, and then there are other job IDs. This job is still pending. You can also click on instance QPUs to see what quantum computers are available to you for free use. So I have access to IBM Kyiv, Brisbane, and Sherbrooke, and all these three are 127 qubit quantum computers. If you want to take a look on all IBM quantum computers, you can click on all QPUs, and you can see other quantum computers that are available in paid IBM accounts. For example, there are 156 qubit quantum computers available as well. Okay, so let's get back. Installation has been completed. Perfect. So let me start by importing quantum circuit from qiskit. From qiskit, import quantum circuit, and draw the circuit. So this time I need to have a quantum circuit with 2 qubit, but also 1 classical bit. I need the classical bit because I want to measure one of the qubits, and at the end we can draw the circuit. So you can see there are 2 qubits and 1 classical bit. So we can draw the circuit easily. And let me just copy my commands, and you see this is a simple circuit where there's this control X, header mod, and a control Z gate. But I have to measure this last qubit, so I need QC measure, and I want to measure one qubit number 1. The indexing start from 0 and want to put the results on the classical bit 0. Okay, perfect. And I also want to initialize this qubit Q0 to an arbitrary state, and for that let's import from qiskit, import quantum info as QI, and let's also import numpy as NP, because I need to prepare a general state vector, which I can do using state vector command in QI, and let's say I initialize to square root 0.2, square root, which is available in numpy 0.8, and then we initialize our quantum circuit with SV, and I want to initialize qubit 0. Okay, so there is this error, SQRT. Perfect. So we have initialized this qubit Q0 to state psi state vector this, and then there's this measurement happening. And let's now copy the code that we already have for Aer Simulator, and let me just explain each line what it does. So I have this function transpile imported from qiskit, and then there's this sampler v2, sampler version 2, that we have imported from qiskit IBM runtime. So this sampler is essentially an efficient way of running this entire circuit and then measuring it once at the end. So sampler runs the circuit and measure once at the end. And then we have this Aer Simulator. So I instantiated the Aer Simulator, and then I constructed this sampler Aer function, which has this mode argument set as Aer Simulator. So we can actually use this sampler v2 to run on quantum computer as well, and in that case we will change the mode to the quantum computer. And then before we do anything with the circuit, we need to transpile the circuit to the language that the Aer Simulator can understand. So we transpile and tell the transpile function that the backend is Aer Simulator. So backend is essentially the computer or simulator that has to be used. Okay, so we now have our transpiled circuit, and our sampler is also now run. And let's now put the most important command perhaps, and that is this one, that the syntax to run this primitive unified blocks is this, that we have sampler air.run method, and then we provide these pubs. So this is the first pub where I give the circuit, and then the second argument is the parameters, but since circuit has no parameters, I wrote none, and 100 means I have to run it for 100 times or for 100 shots. Similarly, there's another pub. So this second pub tells us that to run the same circuit, and by the way, in the second pub you can have another circuit. For example, you can construct two circuits here, and then the second pub can have another circuit. All you need to do is transpile the other circuit as well. So maybe there's a QCTR2, and then this has to be run 1000 times. And I have just written here the flow that we have to provide circuit, parameters, and the number of shots that the circuit has to be run. Okay, so once we have run the job, we can retrieve the results from it using dot result method. So this dot result will extract the results from this job, and then since there are and suppose I want to get the counts, like how many times did 0 was measured and how many times 1 was measured. So then what I can do is from these results I access the 0th pub. So 0 mean the first pub, this pub, and then dot data, that from the results get the data, and from the data I'm looking at the classical register C. So this is this register C that is named here. If you change the name here, then you will have to change the name here as well, and then dot get counts method will get the counts out. Okay, so the counts are in counts 100, and let's now plot the counts, which we can do using this plot histogram method. So from the qiskit dot visualization we can import plot histogram to plot histogram, and if you want to plot the probability, you can use the plot distribution. Okay, so it means that when the circuit ran 100 times, 14 times it measured 0, and 86 times it measured 1. Okay, and if you want to see the results for the second pub, all you have to do is change this 0 to 1. So instead of the 0th pub, I am now accessing the results of the first pub and calling these results counts 1000, because this circuit was ran for 1000 shots. Okay, so let's see. Okay, when I ran this, so 0 was measured 193 times and 1 was measured 800 times. So you see, as the number of shots are increasing, we are approaching the probability that we should. This state was initialized to 0.2 and 0.8. It means so from 1000 this should have been measured 200 times if the state transfer is correct, and this should have been measured 800 times. Alright, so let's now see how to run the same circuit on IBM quantum computer. To run the circuit on IBM quantum computer, actually we only need to change a few things, and let me just show the most simple way. So what we do, we actually don't need it, we already imported transpile. So from qiskit IBM runtime, I'm importing sampler v2 and this qiskit runtime service. So with this qiskit runtime service, I can tell Python how to connect to IBM quantum computer. So for that I specify channel, that channel is IBM quantum, and then I also have to give it token in the inverted bracket, and the token will link this file with my account. And for that, let's go to my account and go to dashboard. So on the dashboard you will see there's written API token. So you can copy the token from here and then come back here and paste it here. So when this token is run, IBM service will now link this, whatever happens with IBM service will actually run in your IBM account. And suppose I want to use one IBM computer. Let's say I want to use IBM Kaiv. So now this is the method dot backend, that I can get this quantum computer by using dot backend with IBM service. So with IBM service dot backend, I give it the name of computer. I can only give one of these three names because these are the three quantum computers that are available to me: Kaiv, Brisbane, and Sherbrooke. But Brisbane is offline, and Sherbrooke is usually busier than Kaiv because Sherbrooke have less errors, like only 3 10 power minus 3, and this 2 qubit error is 4.27. So people like to use this Sherbrooke more than Kaiv. So let's use Kaiv right now. And then another important difference you see from the simulator is this, that I'm now instantiating my sampler V2 with mode IBM QCOM, where this IBM QCOM is this IBM service IBM Kaiv. So let's run it. Perfect. So now I have my sampler pointed towards IBM quantum computer, and we have our backend. So let's now submit the job to the quantum computer. But before we do that, there's one important thing that we have to do, and that is that we have to transpile our circuit according to the quantum computer. Because you see, this quantum circuit QC that we have put here is written in this qiskit language, but we have to transform into a set of instruction that the quantum computer can understand. So for that purpose, we need to transpile the circuit and tell it that the backend is now IBM QCOM. So I have now this circuit here, and after this, it's the same pub method that I can give as many pub as I want. So circuit, there's no parameters, so none, 100 shots, circuit, no parameters, and 1000 shots. Okay, and let's run it. So now the job is submitted to IBM quantum computer, and I can come back to the dashboard and see that there's a job that is already here, and I can actually print this job ID right in my file as well. So let's say job, let's print job underscore IBM dot job ID. So this is the job ID that has been running over there, and I can access those results again, because this can sometimes take hours or days. We have submitted the job and it's gonna take some time, and what I have actually done is already submitted a job over here, this job ID starting with C ending with 0, and what I can do is and actually there is one before. Let me use this one right here and access the results that are already there. So with this, I'm now able to bring all the results from there. And remember, this IBM service is still being used because I have to specify where to get the job from. So this is the job ID. So again, through IBM service, which I have already instantiated here, it knows that it has to go to my account with this token, and from there with this job ID, it gets the results. And once we have the results, then the process is exactly the same as in the simulator. So from the job, I can get the results out, and for the 0th pub, there are two pubs. So there's this pub and then the second pub. So for the first pub, I can get the results like this. All right, so you see that the results are quite noisy. Actually, it seems like the results are for something else. This is 100. Oh, so this is another circuit, not the one that I intended. Let's see if our own job has run. So I can copy the results. Oh, perfect. This is actually even better. So let's just take this job that we just submitted. We got lucky that it ran quickly. Okay, so see, this is the same job ID that we just submitted, and for this, all right, so you see 0 came out 28 times and 1 came out 72 times. And if you want to see the results for the second pub, let me put 1 here, and for the second pub, the results are 0 187 times and 1 803 times. And actually I can compare the results for this IBM and for, let's say, this counts 1000 for the Aer simulator. Let's do plot histogram as counts 1000 and counts IBM. Okay, so now we have these plots side by side, and we can see that the IBM's results are a little bit more erroneous, and the simulator results are closer to what we expect, which is fine because the IBM quantum computer unfortunately are a bit noisier right now. So let's give it simulator, let's give it a legend and IBM Kai. Okay, so these are the results, and you can actually also plot their probability distributions. All you have to do is just change the histogram to distribution, and then now we have plotted the probabilities. It's called quasi probability because it's not a true probability. It's essentially the frequency, because what it does, it divides these counts by the total number of shots. So the experiment was run 1000 times, so this plot distribution function divided these counts by 1000 and obtained these frequencies or probabilities. And so this essentially shows the function of this circuit as a qubit state transfer function. And along the way we also learned how to run primitive unified blocks on simulator like this, again to repeat circuit parameters shots. And then we have exactly the same way of running these pubs on the quantum computers. All we have to do is, before we send the job to quantum computer, is like two things. One is that transpile the circuit according to the quantum computer. And remember, if you change the quantum computer here, let's say to Sherbrooke, you will have to transpile again and transpile it according to the Sherbrooke quantum computer. And the second thing is that this sampler V2 has to be properly instantiated to the required IBM quantum computer. So for simulator, this mode was simulator. For IBM quantum computer, this mode is IBM QCOM. So with this quick introduction to running primitive unified blocks on simulator and on quantum computers comes to an end. You can download this Jupyter file from GitHub and practice as you like. But please change the token with your token. What I am actually going to do quickly is regenerate the token, so that even if you use my file, this token will not be useful anymore, and you will have to put your own token. So with this, thank you very much for watching this.